Welcome to the Aurelion Vortex Lens Platform, a revolutionary leap in propulsion. Conceived by Colonel James Edward Hartman, ADC Kentucky Colonel. This system reimagines Ampere's law, blending electromagnetic theory with dynamic, tunable control. The journey begins with a bold question. Can we mimic gravity and achieve controlled flight using only spin, pulse, and field alignment? Today, we'll explore the technical scrolls, schematics, and operational logic behind this modular lenticular saucer. Let's set the stage for a deep dive into the science, engineering, and vision that powers this unique craft. At the heart of this propulsion system lies a fresh interpretation of Ampere's law. Traditionally, this law describes how electric currents generate magnetic fields. Here, we treat the saucer's rim as a dynamic current loop, pulsed in carefully timed bursts. These pulses sculpt magnetic fields that interact with Earth's ambient directional flow, creating zones of lift, drag, or stability. By controlling the direction and frequency of these pulses, the saucer can hover, ascend, or descend, all without traditional combustion or mass ejection. This is electromagnetic field engineering at its most creative. The Aurelion saucer features a dual-disc, lenticular architecture. Around the rim, segmented toroidal coil arrays are precisely positioned for independent pulsing. This modular design allows for directional thrust, field shaping, and rapid adaptation to changing environments. Internal gyroscopic stabilizers maintain orientation, while the central vortex lens focuses and modulates entropy flow. Every subsystem is engineered for redundancy and operational clarity, ensuring the craft can transition seamlessly between hover, ascent, descent, and full vector travel. Spin direction is the dial that tunes the saucer's behavior. A leftward spin opposes Earth's flow, generating buoyant lift and simulating anti-gravity. Rightward spin aligns with Earth's field, reinforcing descent. Alternating spin neutralizes net field interaction, enabling stable hover. By introducing phase delays between coil activations, the saucer can steer, stabilize, and even perform diagonal or lateral maneuvers. This spin phase logic is the key to full 360 degrees control, making the craft agile in any environment. Pulse modulation is the secret sauce of the Aurelion platform. By varying the amplitude and frequency of current pulses through the segmented coils, the craft can control field strength, direction, and thrust. Low-frequency pulses maintain altitude for hover, while high-frequency bursts trigger rapid ascent or descent. This approach allows for smooth transitions between flight modes and precise control over lift and drag. The result is a craft that can bounce, zoom, or glide with electromagnetic finesse. Circling the saucer's rim are toroidal coil arrays, each capable of independent activation. This segmentation is crucial for directional control. By pulsing specific coils, the craft can vector thrust in any direction. The arrays are engineered for redundancy, ensuring that even if one segment fails, the others can compensate. This robust design supports both rapid maneuvering and stable, energy-efficient flight. Gyroscopic stabilization is essential for maintaining orientation during rapid spin phase transitions. The dual-disc structure acts as a massive gyroscope, dampening unwanted pitch and yaw. This allows the saucer to remain level even during aggressive maneuvers or sudden changes in thrust direction. The result is a craft that feels stable and responsive, no matter the operational scenario. Subsystem blueprint details every layer of the saucer's architecture. From the segmented coil arrays to the central vortex lens, each component is mapped for clarity and operational fit. Internal cutaways reveal the routing of entropy flow, the placement of gyros, and the logic of pulse modulation circuits. This blueprint is the foundation for all technical scrolls and operational posters, ensuring every engineer and operator understands the craft's inner workings. The saucer's behavior is governed by a matrix of spin direction and pulse pattern. Hover mode uses alternating spin and low-frequency pulses for stable levitation. Ascend mode employs leftward spin and high-frequency bursts to generate buoyant lift. Descend mode uses rightward spin and sustained pulses to reinforce Earth's flow, accelerating descent. Crash mode is triggered by rightward spin with overpulse, collapsing the field for a hard landing. Each mode is engineered for rapid transition and operational safety. Let's walk through the core operational scenarios. In anti-gravity lift, leftward spin and pulse bursts create upward bounce, enabling tunable ascent. Gravity mimic descent uses rightward spin to align with Earth's flow, resulting in rapid, controlled descent. Hovering stability is achieved through alternating spin and low-frequency pulses, maintaining altitude with minimal energy. Omnidirectional travel leverages segmented coil activation and phase spin to steer the craft in any direction, offering unmatched maneuverability. Schematic overlays the saucer with labeled coil zones, spin vectors, and pulse modulation paths. Each segment is color-coded for clarity, showing how independent coil activation steers the craft. Flow alignment indicators reveal how the saucer interacts with Earth's ambient field, providing real-time feedback for operational adjustments. This visual is essential for both training and archival documentation. Every technical scroll and schematic is attributed to Colonel James Edward Hartman, ADC Kentucky Colonel. This formal recognition ensures that the vision, theory, and engineering behind the Aurelion Vortex Lens Platform are preserved for future generations. Authorship is embedded in each artifact, honoring the origin of this groundbreaking propulsion concept. The technical report begins with an executive summary, outlining the novel propulsion system based on Ampere's law. The lenticular saucer achieves hover, ascent, descent, and full 360 degrees maneuverability through spin phase modulation and pulsed electromagnetic thrust. By aligning or opposing Earth's directional flow, the craft mimics gravitational effects, all while maintaining modularity and operational safety. Ampere's law is reinterpreted for dynamic propulsion. The magnetic field generated by toroidal coils is proportional to the time-varying enclosed current. By treating Earth's ambient vector field as a gravitational analog, the saucer's pulse modulation alters field strength and direction, simulating lift or drag. This theoretical foundation enables the craft to operate in any environment, from air to sea to space. The saucer's architecture features a dual-disc design with independent spin control, segmented toroidal coil arrays, and gyroscopic stabilizers. Each subsystem is mapped for clarity, from the central vortex lens to the entropy-modulated propulsion core. This modular approach ensures redundancy, adaptability, and operational clarity across all flight modes. Spin phase control is the heart of maneuverability. Leftward spin opposes Earth's flow for lift, rightward spin aligns for descent, and alternating spin neutralizes for hover. Phase delays between coil activations enable steering and stabilization, allowing the saucer to perform complex maneuvers with electromagnetic precision. Flight mode's matrix details how spin direction, pulse pattern, and field interaction combine to produce different results. Hover uses alternating spin and low-frequency pulses for stable levitation. Ascend mode uses leftward spin and high-frequency bursts for rapid lift. Descend mode uses rightward spin and sustained pulses for accelerated descent. Crash mode is triggered by rightward spin with overpulse, collapsing the field for a hard landing. Each mode is engineered for rapid transition and operational safety. In anti-gravity lift mode, leftward spin and pulse bursts create upward bounce, enabling tunable ascent. The saucer's field opposes Earth's flow, simulating anti-gravity without mass displacement. This mode is ideal for rapid takeoff, obstacle avoidance, or vertical repositioning in complex environments. Gravity mimic descent uses rightward spin to align with Earth's flow. The stable disk acts as a reference, while the other accelerates downward. This mode enables controlled, rapid descent for landing, emergency drops, or tactical repositioning. Field collapse protocols ensure safety during high-speed impacts. Hovering stability is achieved through alternating spin and low-frequency pulses. This neutralizes net field interaction, allowing the saucer to maintain altitude with minimal energy. Gyroscopic dampers and feedback loops ensure the craft remains level, even in turbulent conditions or during rapid vector shifts. Omnidirectional travel leverages segmented coil activation and phase spin to steer the saucer in any direction. By pulsing specific coil segments and introducing phase delays, the craft can move laterally, diagonally, or even perform complex maneuvers like rapid turns and evasive actions. This capability is essential for both exploration and tactical operations. Lens array focuses incoming signals and stabilizes vortex harmonics. Concentric modulation rings and radial stabilization tubing link the diaphragm to the luminal vortex centrifuge. Subluminal dampener gyros balance internal spin phase transitions, while the entropy-modulated propulsion unit anchors the entire system. This poster is essential for subsystem training and archival clarity. Entropy dampening and pulse harmonics are managed by the secondary lens suite, thermal ergostabilizers, and internal lens aperture. Focused signal transmission creates a luminal path through the core, while the pulse harmonics chamber balances segmented coil harmonics and spin phase transitions. The entropy-modulated propulsion core drives all motion, ensuring operational integrity. Vortex deployment scroll details lens array functions, field dynamics, entropy flow modulation, and gyrostabilization. Hover lift stability is achieved through segmented coil harmonics, while operational parameters are formatted for archival realism. This scroll is the definitive guide for deployment and field behavior. The saucer hovers above the ocean's surface, demonstrating electromagnetic pulse interaction and inclined spin phase for waterborne lift. Pulsed buoyancy vectors counteract water pressure, while coil emissions create a helical field pattern. This mode adapts the propulsion system for aquatic environments, ensuring smooth travel and rapid surfacing when needed. In sea mode, electromagnetic pulses interact with polar water molecules, generating lift and directional thrust. Coil segmentation allows for precise maneuvering, while alternating spin creates neutral buoyancy zones. The saucer's field generates localized cavitation bubbles, reducing drag and enabling smooth submerged travel. Airborne acceleration mode uses high-frequency electromagnetic bursts tuned to air density. Pulse bursts compress surrounding air, creating lift pockets, while the spin phase vector tilts the saucer for rapid ascent. The craft rides a self-generated plasma envelope, enabling supersonic travel without a sonic boom. Land skimming mode leverages gyrolock stabilization for terrain-adaptive glide. The saucer hovers just above the ground, using segmented coil activation and pulse modulation to maintain altitude and avoid obstacles. This mode is ideal for rapid, low-altitude travel across varied landscapes. In orbital deployment mode, the saucer glides above Earth's curvature, using pulsed multi-wavelength fields for vacuum traversal. Alternating spin stabilizes the craft in microgravity, while segmented coil activation maintains orbital velocity. The field envelope acts as a thermal buffer, protecting internal systems from radiation and extreme temperatures. Microgravity traversal leverages alternating spin and coil segmentation for directional thrust in zero-G pulse bursts, create momentum packets, enabling movement without combustion. Gyroscopic stabilizers maintain orientation, while the field envelope shields the craft from radiation and thermal extremes. Interplanetary navigation is achieved through coil traversal logic and gyrophase vectoring. Segmented coils pulse in planet-specific sequences, adapting to gravitational gradients. The saucer can transition between planetary atmospheres and deep space, deploying drones for orbital skimming and data collection as needed. The primary lens platform focuses incoming signals and stabilizes vortex harmonics. The vortex diaphragm, luminal vortex centrifuge, and subluminal dampener gyros work in concert to regulate entropy flow and maintain operational stability. This schematic anchors the Aurelion archive, providing a clear reference for subsystem integration. The entropy-modulated propulsion core is the heart of the saucer's motion. It regulates heat, entropy flow, and signal convergence through a suite of thermal stabilizers, internal lenses, and pulse harmonic chambers. This core enables the craft to adapt to any environment, from deep sea to outer space. All schematics, scrolls, and posters are part of the unified Aurelion Vortex Lens Platform. Modular subsystems enable rapid adaptation to any operational domain, while the central intelligence coordinates entropy-modulated propulsion and vortex lens control. This integration is the key to the craft's versatility and resilience. Refined lens array poster features improved line weight, color contrast, and radial precision. The vortex diaphragm and luminal centrifuge are rendered with archival clarity, while all labels are corrected for spelling and operational fit. This poster is the definitive reference for lens array and centrifuge logic. The entropy dampening poster is rendered with full archival clarity, internal cutaways, and corrected labeling. The secondary lens suite, thermal stabilizers, and pulse harmonics chamber are all clearly depicted, ensuring operational clarity and subsystem training accuracy. The operational scroll details lens array functions, entropy flow modulation, and gyro stabilization. Hover lift stability is achieved through segmented coil harmonics, while all operational parameters are formatted for archival realism. This scroll is the definitive guide for deployment and field behavior. Field collapse is triggered by overpulse or sustained spin alignment, causing magnetic field destabilization. Coil arrays enter a null phase, ceasing lift generation, and the saucer descends rapidly. Emergency protocols include pulse dampening, coil reversal for last-minute hover, and impact vector prediction for safe landing. The saucer's rim is divided into 12 trapezoidal coil segments, each independently pulsed for directional thrust. Pulse bursts are timed to spin phase intervals, enabling smooth vector transitions. The velocity control formula, derived from Ampere's law, governs real-time maneuverability. From the modified Ampere's law, the resultant velocity vector is determined by coil current, pulse timing, and spin orientation. This gives the saucer a velocity field, not just a force vector, allowing for smooth, tunable motion across all operational domains. The crash descent schematic depicts rightward spin alignment with Earth's flow, field collapse, and downward acceleration. Segmented coil activation, impact trajectory, and gyroscopic stabilizers are all visualized, ensuring clarity for emergency protocols and operational safety. Internal cutaways reveal the routing of entropy flow, placement of gyros, and logic of pulse modulation circuits. These visuals are essential for subsystem training, maintenance, and operational clarity, ensuring every operator understands the craft's inner workings. The full vector control schematic showcases inclined spin phase geometry, segmented coil arrays, and directional arrows for hover, ascend, descend, and lateral thrust. Ampere's law is adapted for velocity through pulsed spin phase, with authorship embedded for archival clarity. Every schematic, scroll, and technical report is rendered with archival clarity and full authorship embedded. Spelling, labeling, and graphic enhancements ensure each artifact meets the highest standards for operational fit and historical preservation. This legacy is secured for future generations of engineers and visionaries. Aurelion Vortex Lens Platform stands as a testament to visionary engineering and the power of reimagined physics. Colonel James Edward Hartman's concept unites electromagnetic theory, modular design, and operational clarity into a single, unified craft. This legacy will inspire future generations to push the boundaries of science, technology, and exploration.